All right, welcome back. We're going to look at some more proofs from the first week of in-class problems. Here we're talking about set containment. We're going to do two problems here. The first one tells us that we have two sets R and S whose union, right? So that's all the elements that are in R combined with all the elements that are in S. We know that that union is equal actually to the original set R. And the question is what can we conclude about the set S? So let's try to draw a picture. So first, you have this set R. And normally, if we draw a picture with another set S, we draw these little Venn diagrams. And there's a few options, right? So let's draw some of these options. So one of the options is that they have no intersection whatsoever. There's nothing in common, and you could put them together. Now, if this was the case, you can see that there are going to be elements of S that are not in R. So when I do the union, right, the union of course would be everything. I'm going to get some new elements, right? So the union will contain things not in R, which means you cannot have equality. Because remember, what does equality mean? Equality means every element of R union S is an element of R, and every element of R is an element of R union S. Okay, so here, when you looked at R union S, you would have an element which was not an element of R. So this top line would fail. Okay, what's another picture we could draw? Well, another one we could draw is if they do have some sort of intersection. So there could be an R and there could be an S. And again, though, if the intersection looks like this and you have some stuff outside and you have some stuff inside the intersection, again, when I take the union, which will give me everything, right? This whole thing will be R union S. I will get an element in the union which was not originally in R. So this is not the correct picture either. Okay, here is another picture we could draw. So I'm going to draw my S and I'm going to put the R completely inside. Okay, well, so I got some points here in R and then I got some points which are in S but not in R. Okay, what would be the union here? Well, here the union is everything in this whole set. Actually, this S would be the same as R union S. When I put it together, right, I don't get anything new because this R was already inside of S. Okay, so again, though, I have an element of S which is not in R, so I have an element of the union which is not in R. Okay, so we got to go to the final picture, the last one, which is going to look very similar, only I swapped the role of R and S. So now if I have S completely inside of R, now when I take the union, they're actually the same thing. I'm not including anything new to R when I include S, because S was already inside of R. So every element of the union is an element of R. All right, so that's how we can see it with a picture. Let's go back up here and do this a little more precisely, right? Maybe we're missing some combination, although we're not. So every element of R is an element of R union S. That's actually always true, right? What are the elements of R union S? They're the elements of R combined with the elements of S. So if you have an element of R, it's in the union, right? So this second line is always true. Always true. Okay, so what about this first line? Well, that may not always be true, as we saw. This failed, in fact, in four of these, or three of these four situations. So what does it require? What's needed for R union S, right? For every element of R union S to be an element of R? Well, we already know the elements of R are elements of R, but we need the elements of S, right? These are the ones we combine with R to make the union. We need that every element of S is an element of R. So if we were going to write this down precisely, we could already say, well, every element of R is an element of R union S. And we know that R union S is a subset of R if every element of S is an element of R. i.e., so this is the condition, right? We need something to conclude about S, i.e., S is a subset of R. All right, so whenever you have two sets and you take their union and you get back one of the original sets, the other set must be a subset of the original set. Okay, so in this case, S has to be contained in R. Okay, well, what about the intersection, right? This is basically the same property now, except I'm saying intersection instead of union. Okay, well, again, what does it mean for these two sets to be equal? Well, we say every element of R intersect S is an element of R, and every element of R is an element of R intersect S. Now, last time, it was the second statement that was always true. Every element of R is an element of the union. This time, it's actually going to be the first one, which is always true. Okay, let's see why. So every element of the intersection. So what is the intersection? The intersection is all of the elements that are both in R and also in S. Well, what's the first half of that sentence, right? Both in R. Ah, they're in R, right? So we're looking at elements that are actually, we know to be in R. So this first statement is always true. Okay, so the only thing we now have to determine is when could the second statement be true, that every element of R is an element of R intersect S. Well, what's required for R to be, for an element of R to be an element of R intersect S? Well, to be an R intersect S, you have to be both in R. Okay, we're good. We got that. And you have to be in S. So the only elements that are going to work are ones which are in R and in S. So we're looking for the elements of R that are also in S, but we want every element of R to be in S. Okay, what does that mean? Every element of R, so this is equivalent to saying every element of R is in S. That's what, for this all to work out, right? That's what we need. Well, that means R is a subset of S. Now, if we go back to the pictures, we can see this. Here's our first example where we say, okay, they have no intersection whatsoever. That intersection is clearly not equal to R, right? As long as R is not itself the empty set. Okay, what about the second one? Well, here we have an intersection, but it's not equal to R. We have points in R that are not in the intersection. So this picture's no good. How about this one? That was the winner before. Well, the intersection of R with S, well, that's all the things that are in both R and in S. That's just this S here. Well, now I have things in R that are not in the intersection. So this picture doesn't work. Okay, so finally, let's look at this picture. Now when I take the intersection, it's the R that's the intersection, right? All the things that are in R and in S, it's just the elements of R. And so sure enough, look at that. R is equal to R intersect S. And so my R in this situation is a subset of S, right? Whereas over here, S was a subset of R. All right, so there we go. It turns out that these sort of statements, right? R union S equals R implies that S is a subset of R, and sort of this dual statement with intersections are really, really useful and handy in working not only in set theory, but in algebra in general. It's not even restricted to algebra, right? You can go to just about any area of math. It's definitely the sort of thing where you want to not only know this argument, but even have these statements down so that you can just quickly access these pictures in your mind, all right? Because we're going to use that all the time.